Thank you for coming today. I want to make sure that we thank you for your business on behalf of my brother, my cousin, and a multiple generation. We are transitioning into multiple generations to make sure that Liqui-Grow continues to go. But we thank you for your business. Today's presentation is designed to, as we mentioned, the LEAD Academy, which is Liqui-Grow agronomic leadership and development, and basically what I want you to all know is the reason why we've had the speakers here is we've gotten some feedback that would say grain marketing is important, understanding what's going on in the world of fertilizer is important, and it's been very topsy-turvy. I'll let Jason explain this later. We're not here to basically solve any of the concerns or nervousness that you might have about the future, but we want to add more depth to understanding why things are the way they are. And then Jake's going to finish up with some agronomic updates as it relates to why we do what we do. But most importantly, we're here to educate, we're here to support, we're here to provide your farm customers or yourselves a higher ROI for your investment, whether it be for seed, crop nutrients, or crop protection.
So Jake is going to speak now on the agronomy side. We always like to give you a quick update going into fall. His titles are always really scientific and scholarly to me. So he's going to talk about why nutrients work really well together and how you're going to benefit from that. And then we're going to talk about our new exact strip application technology. So.
Yes, thank you, Katie. Appreciate that. I'm timing myself, Katie. Okay. All right, well, we better get started. The food's going to be here shortly. So I probably ought to introduce myself a little bit because there are some unfamiliar faces, particularly the students there in the back. So I grew up on a family farm, well, my grandpa's farm, about 150 miles south of here in this very river bottom. So I feel like I'm at home, I guess. I went to Northwest Missouri State University, studied ag there, I guess because I didn't know anything else at the time. But I enjoyed that quite a bit, so much so that I decided I wanted to go further on in college. So I went down to Oklahoma State and I got a master's degree in plant and soil sciences. I then worked at DuPont Pioneer for about 4.5 years as an agronomy research manager most of that time. I guess the first 9 years of college was so fun, I thought I'd go back for some more. So I went back to school after that for a few more years, and I've been with Twin State Liqui-Grow for 7 years now, and I truly love working for the Tinsman family. It's a great family-owned company. I mean that wholeheartedly. If you're not a current customer, I would highly encourage you to come into the Twin State family because it's a great place to work with a lot of great people. So very happy to be here, and want to thank you for your time today to listen to me. So on to the presentation. So what we're going to talk about today is we're going to talk about two different subjects that are very well related. Okay, so the first thing we're going to do is we're going to review why we've done what we've done from a fertilizer application point of view for many years. And then we're going to segue into how we're going to do what we've done for a long time, only make it a little bit better. Okay, so continual progress, all right? So, and obviously I'm speaking about soil fertility, okay? So I'm going to be very brief about this, but what we do on 90% or so of the acres that we fertilize today is we do something called 15-inch dribble banding. And we do that for two reasons. Number one, we do that because we want to apply nutrients uniformly across the swath width of a floater pass, and that can be important to crop yield, and we're going to get into that. And we also apply this fertilizer in 15-inch bands on the soil surface. The farmer may or may not incorporate that. It just depends on what he does with tillage, okay? And so it's the banding part that can be very important for maximizing nutrient use efficiency. In other words, getting more yield for every dollar spent on fertilizer, and of course, maximizing crop yield, okay? So, you know, so between the uniform application and banding, those two things can be important for ROI and yield, all right? So we're going to talk about that first, and then we're going to go into how do we use placement to make those same two things I just talked about even better for ROI and yield, all right? And that's what we're calling our exact strip placement technology, and we'll kind of get into the details of that. So that's what we're going to cover today, all right? So let's get into the first question of the day. So, you know, I spend a lot of time doing research and development stuff, but the other half of my job, I spend a lot of time with you guys, with our salesmen, with our customers. And so I get asked lots of questions all the time. It's my job to answer questions, and one of the simple questions that gets posed to me probably once a week is, well, you know, is banding really necessary, or how important is banding? And my answer is, it depends, right? I mean, everything we do in agronomy, there isn't one management factor that we do that makes a difference every single yield in every field. It just doesn't work that way. It's complicated, right? Nitrogen fertilizer doesn't even increase corn yields every single year in every field. Most of the time it does, but not all the time, okay? Because the soil can supply a lot of nitrogen at times, all right? So no, not all the time does it help, but many times it does. In fact, I would say banding rarely, if ever, decreases yields. And with fluid fertilizers, they're very flexible, and we can band them. Why wouldn't you? That's how I look at it, okay? But let's talk about some of the specific environments where I'm very confident banding can help, and why it matters, all right? So first of all, we see very consistent yield increases over broadcasting and low testing P&K soils, okay? So if you have soils that are moderate to low testing, you know, those are the environments where we need to be really fussy and really efficient with our nutrient inputs, okay? And banding can help with that efficiency, and we're going to talk about why next. So part of the reason why is if you have soils that have a pH of above 7.3-ish or below 5.3-ish, it's at those, the opposite ends of the spectrum is where we have phosphorus tie-up, for example. So at pHs above 7.2, 7.3, we have phosphorus that gets tied up with calcium, and that means it's not crop or plant available. At pHs below about 5.3, we have phosphorus that gets tied up with iron and aluminum, and it's not plant available, okay? So those are some very specific situations where banding is very important with an exclamation point, all right? And so the thing I would say is, no, we don't try to manage our soils in that pH environment that's either too high or too low, but it happens, okay? Cash rent situations, we don't want to pay for the lime, it happens. High input prices, we want to wait a year to put that lime on, it happens. Some soils naturally have a high pH, and there's nothing you can do about it. In fact, I was with a customer, Jess, we were with a customer the other day, and I kind of asked the question, he asked me this very question, well, how important is banding? And I said, well, what are your soil pHs? And his response to me was, well, they're great, they're good. Okay? We continued to talk, and it boiled down to, I can't help you anymore unless you send me your soil test so I can take a look at them and see what I'm working with here. So he did. I drank a cup of coffee on Saturday and looked at those soil tests, and guess what? About 15% of his acres, the pH was 7.3 to 7.7. So he had good pH. Oh yeah, too good a pH. All right. So my point is that, you know, we try to manage pH in an area where it's optimum for nutrient uptake and yield, but it doesn't always happen. All right. With potassium, that one's a little more complicated. But soils can fix potassium too. They can make it not plant available. In dry conditions, when you have clay in your soil, which also has some level of clay, you end up getting clay stuck between interclay layers, and the crops can't get it out. Okay, so the more clay you have, and it gets down to the very specific mineralogy of your clay, but generally when you have more clay, you have the ability to trap that potassium between those interclay layers. When the soil gets moist again, some of that comes out, but some of it can be bound up and stay in between those clays for years to come, okay? So banding is a way to physically separate the fertilizer from those inner clay layers and make it more plant available, okay? All right, and so next, this one's not as well known or understood, but I think it's very, very important, particularly for you no-tillers or you folks that are just doing some light tillage with a one-pass tool perhaps. Banding physically helps move nutrients down deeper in a limited till situation, right? So if you're a no-tiller or you do very limited tillage and you're not incorporating nutrients, what happens is plants, most of the mineral nutrients are taken up in the top 6 inches of the soil, but those roots that go down much deeper, they will extract nutrients from depth. They will put those nutrients in the vegetative part of that plant. When that plant dies and senesces, those nutrients eventually work their way back out of that crop residue and is deposited on the soil surface, and you end up with a layer of nutrients, very dense nutrients, about 1.5 inches to 2 inches thick on top of the soil surface. Now when it gets dry, that's a problem because you need soil moisture to get those nutrients to move toward the roots and for those roots to take it up. So you need soil moisture, and in a no-till situation, if you don't have a lot of soil moisture in that very top layer, that can become a problem, right? So this study was done by USD ARS scientist. His name is Dr. John Kovar. I believe he still works in Ames, Iowa, where this was done. So he had a theory that, we all know the soil is negatively charged, right? So the soil is negatively charged. Cations, which is potassium, phosphorus, zinc, for example, those are all cations. They're positively charged. So when you apply potassium and zinc, for example, to the soil, because it's negatively charged, they're held very tightly and they don't leach and they don't go anywhere. So that's a good thing, right? But the soil only has so much negative charge, if that makes sense. So in other words, if you band cations in a very tight band on the soil surface, you're going to overwhelm the ability of that soil to hold all those nutrients in the very top inch. And some of those nutrients are going to bleed down or leach down until the soil has enough charge to stop that movement, all right? So this is just a study where Dr. Kovar radio-labeled some phosphorus. He applied it on the soil surface 2 inches from the plant. And you can see that a good chunk of that phosphorus moved down about 3.75 inches. So banding is a way to help get those nutrients moved down deeper within the soil itself. All right, so that's a very important topic. This has actually been studied more on a field scale, in a field scale type environment, and we clearly show that banding is a way to help move those nutrients down and can help increase yields in limited tillage situations relative to broadcasting just on the soil surface. Okay, and now the last one that is even less well understood, but is extremely important, I can't emphasize that enough, to getting yield increases from banding crop nutrients, and that's called co-application. So when you band nitrogen, phosphorus, potassium, sulfur, zinc together, there's some interactions that go on there that are very important for increasing crop nutrient availability, okay? And that's what we're going to talk about next. And we're going to spend most of our time on that because it's not very well understood, but yet it's a very important factor that needs to be taken into consideration. Okay, so before we go there, well, we're going to go there now, but before we get to this slide, I brought up in the beginning that banding doesn't always increase crop yields. And even in university-type studies that have been published in scientific journals, it's clear there are cases where banding in those studies did not increase corn yields. But yet there are other examples where absolutely banding increased corn yields. And these, again, are studied, peer-reviewed, published studies, okay? So even among academics, you could say it's debatable whether or not banding is better than broadcasting nutrients, all right? But this guy in 2018 what he did is he summarized all the literature out there on banding versus broadcasting crop nutrients, And that'll tell us, on average, what would we expect. But what that also does is it helps you understand what were the factors involved in study A where there wasn't a yield increase versus what were the factors involved in study B and why was there a yield increase. Okay, and that's very important to help us understand under what conditions would we expect a yield increase from banding. Okay, so the data here is from lots and lots and lots of studies dating back to the late 1960s until the time this study was published in 2018. All right? So they found lots of things, but the most significant thing that they found is back to this idea of co-application, or this interaction between these nutrients. All right? So we're going to go through several reasons why this happens, but we have to start somewhere. Okay? So I want to point your attention to so first of all, this line here, this would be the broadcast treatment, okay? So if the circle is on top of the line, that means that broadcast and banded nutrients yielded the same, okay? But if the dot is to the left, then that means that banding was better than broadcasting, okay? So notice that when you just applied ammonium, or just nitrogen, there was not a yield increase to banding just nitrogen versus broadcasting nitrogen, okay? But notice when you applied urea and phosphorus together, so a nitrogen source with a phosphorus source, there absolutely was a yield increase. Notice that when you applied ammonium and phosphorus together, there was absolutely a yield increase. So that's telling us when you apply a nitrogen source and a phosphorus source together, absolutely banding those nutrients relative to broadcasting at the same rate increase crop yields. Look what happens when we just band potassium together or just band phosphorus together. When we just band potassium or phosphorus alone, they did not report a yield increase. So this tells us that this co-application idea is really, really important to get a yield increase from banding nutrients. Okay? So why might that be? I'm telling you it's very important. So why would that be? Well, there's several reasons why, but we're going to kind of go through these one by one. So it turns out that when you apply nitrogen to the soil, whether it be urea, whether it be anhydrous ammonia, or whether it be ammonium, all those nitrogen sources have to go through a process called nitrification. Okay? So nitrification is the process from ammonium going to nitrate. Okay? And when you apply urea, ammonium, and anhydrous ammonia, that process starts happening, and depending on soil temperatures, it could take a week in warm soils, it could take 5 months in frozen soils. Okay? But nitrification happens. And when nitrification happens, one of the end products is acidity, or hydrogen ions. Okay? And that's important because roots do something called establish an electrochemical gradient. And they need to do that because in order to take up anions like nitrate and sulfate, they have to do this. Okay? So the interior of a root cell has a pH in the low 3s to high 2s. And what roots do is they pump hydroxyl ions out into the rhizosphere, which increase the pH a lot. So you're going to find that if you could measure the pH on the outside of a root, you're going to find that the pH on the outside of a root is in the high 7s to mid 8s, but on the inside of the root, the pH is in the low 3s to high 2s. And that establishes a huge gradient between pH, and it's called an electrochemical gradient, and that's how plants take up anions. Okay? So in order for a plant to take up nitrate, it has to establish this electrochemical gradient. Now, if you think back to one of our conversations we've already had, what happens if we have a pH of 8 on the outside of the root, and we have a phosphorus molecule migrating toward the root, and that phosphorus molecule runs into a pH of 8? It's going to get tied up with calcium. It's going to precipitate as dicalcium phosphate, which is not plant available. So, if you have nitrogen applied in a band with phosphorus, that nitrogen is going to lower the pH of that band, and it's going to help it's going to help counteract the rise in the rhizosphere pH. This study was published in 1977. We've known this for a long, long time. It's very, very clear that this happens. This is why DAP exists, this is why MAP exists, and this is why ammonium polyphosphate exists, which would be our 1032O. We know, and we've known for a long time, that phosphorus and nitrogen together make phosphorus more plant available. The other reason why DAP, MAP, ammonium polyphosphate exists is because phosphoric acid has a pH in the high 2s, low 3s, and that would be dangerous for people to handle, and that would be extremely bad for equipment. It would just eat up equipment. So if you react anhydrous ammonia with phosphoric acid, because anhydrous has a pH of 8 and phosphoric acid has a very low pH, you react those two together and you get a product that has phosphorus that's much more soluble and plant available, and it has a very balanced pH, so it's not dangerous for people or dangerous for equipment. Okay? So, this is an example of zinc. Okay, so what we know about zinc is not very plant available at a pH of 5 or 6, or I'm sorry, zinc is very available at a pH of 5, but that's not an ideal pH for almost every other mineral nutrient, like phosphorus, for example, okay? Phosphorus is very available, Phosphorus is not very available at a pH of 8, at 8.5, but at a pH of 5 it is very available, okay? So this nitrification idea is also very, very important for the availability of zinc. But on top of that, there's a product called ammonium thiosulfate. Ammonium thiosulfate is a sulfur source, and it's a sulfur source that we use, and it just so happens when you apply ATS to the soil, that product has to oxidize into sulfate sulfur. And the end product of that chemical reaction is also hydrogen. So what happens when you oxidize ATS to sulfate sulfur? Again, you get a drop in pH. So when we apply nitrogen, ammonium thiosulfate with zinc, again, we get a reduction in the pH and we get an increase in zinc availability. Okay? So this is actually a study that the gentleman Ken Washburn did before I came here. It was one of the last studies he did. It was done for 3 years near Walcott, Iowa. And what he found is that when you apply zinc by itself with nitrogen, phosphorus, and potassium, you got about a 2.8 bushel yield increase average over those 3 years. When you apply sulfur by itself, you got about a 2.6 bushel yield increase averaged over those 3 years. But when you apply the two together, you've seen an 8 bushel yield increase averaged over those 3 years. So it's this interaction of that nitrogen, that sulfur, and that zinc. It's the lowering of the pH in that band, and it's making the phosphorus and the zinc more plant available. And it's that interaction between those nutrients that increases crop nutrient availability. In this case, we're talking about zinc. So something else that plants do, you know, plants are smart. Plants, they can't see, they can't touch, they can't feel, they can't smell, but they're very good at sensing their environment and taking advantage of what they can take advantage of in their environment. So plants don't seek out high concentrations of mineral nutrients, but when they find them, they invest a lot of root resources in scavenging or mining those high areas or patches of mineral nutrients. And we see this with nitrogen, we see this with ammonium, and we see this with phosphorus. So when plants find that band of fertilizer, they invest a lot of root resources in that highly concentrated area of nutrients, all right? And that's an efficient use of resources for plants. Now, unfortunately, they don't do that with zinc, and they don't do that with potassium. But what do you think might happen if the phosphorus and the nitrogen that the roots do invest resources in is applied with the potassium? Do we think that the potassium would also be highly explored because it's right there with the phosphorus and the ammonium? The answer is yes. Okay, so when you band nitrogen and phosphorus together, roots explore those areas, And because the potassium is with it, they also have to explore that potassium. So this is a study from another USDA scientist. This was done in Texas. So this is another radio labeling study. So in this case, the scientist basically put a marker in the potassium fertilizer, so he could say definitively, of that potassium fertilizer I applied, how much did that crop take up? All right? So he applied potassium by itself, and he only ended up getting about 0.79% of that potassium he applied in that corn crop. But when he applied phosphorus and potassium together, he ended up getting about 1.34%. When he applied nitrogen, potassium, and phosphorus together, he got 1.74% of that potassium that was radio labeled back in that crop. More or less the same thing happened in crop year 2, only in crop year 2, adding that nitrogen didn't increase potassium uptake more than just the phosphorus. But the point is that when you ban phosphorus and nitrogen with potassium, because roots explore that phosphorus and potassium, that phosphorus and ammonium or nitrogen, you also take up more of that potassium because it is with those nutrients that the plants know they have to scavenge and take up. Okay? And finally, this just isn't all mythical and in the peer-reviewed journals and publications. This can play out and does play out in the real world here in eastern Iowa. Okay, so this is a study that I did. This would be the average of 2 locations back in 2020. I actually have 3 more sites in the field right now, and then we'll conclude this study. But what I did here is the control would be 180 pounds of nitrogen. Okay? We have 180 pounds of nitrogen plus zinc. You can see that we got a 3 bushel yield increase. We've got 180 pounds of nitrogen applied with potassium. We got a 4 bushel yield increase. We have 180 pounds of nitrogen applied with phosphorus. We get a 6 bushel yield increase. But when we apply the nitrogen, phosphorus, and potassium together, we get a 15 bushel yield increase. So that would be called synergism. So 1 plus 1 equals more than 2 in this case. So this is just evidence that the phenomena that I'm talking about matters and happens in the real world and can affect your ROI at the end of the day. Okay, we're going to spend not hardly any time on this one, but dry fertilizer machines just have a difficult time uniformly and accurately applying mineral nutrients across the swath of that machine. It's a physics problem, and I'm not going to get into details just because of time today, but we see this time and time and time again in university publications where engineers calibrate these machines and they try to get these machines to apply fertilizer uniformly across their swath. Turns out they don't do a terrible job at very low mineral nutrient rates, but as soon as you get into the rates of a normal type crop removal fertilizer application, they don't do a very good job. And this would be an example of that. So this is an Ohio State publication in 2018. This will be a machine set up to apply fertilizer a 100-foot swath. In the middle 50 feet of that 100-foot swath, there was about 50 fewer pounds of P applied in the middle 50 feet of that machine than on the outsides of that machine. And when you have a soil that's got phosphorus or potassium levels that are moderate to low, in other words, if we would expect a yield increase to applying nutrients, uniform application is most definitely important to maximizing yield and fertilizer efficiency. Okay? So because of all that stuff that I just talked about, in trials that I've done at a bunch of locations over a bunch of years and a bunch of sites, we see about a 5 bushel yield increase for banding fertilizer on 15-inch dribble bands over broadcasting the same rate of mineral nutrients as dry fertilizer. But part of my job is to do research and development stuff, and that means ever improvements or more improvements. How do we continue to perfect the system to get even more yield out of what you're already paying for? All right? So What I'm going to talk about next is something that we're calling exact strips. All right. So when farmers see data, let me back up and say that I go on a lot of calls and I talk to a lot of farmers. Okay, and one of the first questions I get asked when I talk to a farmer that doesn't know anything about 15-inch dribble bands, he says, "Well, can I plant on that?" Well, I suppose it's technically possible, but that's not what we typically do. But I've been asked that so many freaking times that I decided maybe that is technically possible, and maybe the equipment limitations have changed much more than I realize over time. So I thought about that for a number of years, and it turns out that any tractor that's less than 3 years old, that's meant for row crop production, has all the hardware and software on the thing to have something called RTK grade guidance. So RTK grade guidance is sub-inch accuracy from pass to pass as well as from season to season over time. And that's really the kind of accuracy that we need to do what we're going to talk about doing, okay? It turns out that most of these new floaters that we buy has the hardware and software in the machines for them to be RTK ready. So in other words, it's a matter of paying for a subscription, turning the machine on, and they're RTK ready. So what happened, I thought to myself, what happens if we could share guidance lines between the farmer's planter or the strip till bar or the anhydrous ammonia applicator and our floaters? Would it be possible to position this suspension fertilizer very close to where the farmer is going to end up planting? So that's a question that I had that we've thought about and developed over, I thought about it for a while, but we really got serious about trying to do this over the last couple growing seasons. But before we get there, it's data like what's behind me that gets farmers really interested to planting right back on a band of fertilizer, a highly concentrated band of fertilizer. This was a study that was done at the University of Wisconsin, and I might just point out that this was a co-applied fertilizer. 15 pounds of nitrogen, 38 pounds of P, 131 pounds of K. So what they did is they compared fertilizer banded at about 6 inches relative to that same rate of fertilizer broadcasted on the soil surface. And what they found in a multi-location, multi-year study is close to a 12 bushel yield increase on average. Not quite 12 bushel, but very close. So that gets farmers very interested in this idea, right? This is another study from the University of Illinois, similar situation. This would be injected fertilizer at about a 6-inch depth. In this case, they used 30 pounds of nitrogen, 30 pounds of nitrogen, 100 pounds of P, 25 pounds of sulfur, and 2.5 pounds of zinc. In this case, they banded that fertilizer at 0, 3, 6, 9, 12, 15 inches from where they were going to plant, and they had a broadcast treatment. Okay, so what this says is that generally, the closer you planted to that band of fertilizer, the higher the yields went. So it's studies like these that get farmers really interested in trying to plant right back on that band, all right? So, the question we had to answer is, can we technically do this? The other thing that I've ran into and why farmers don't do this more than they do is because we're talking about strip tillage. Strip tillage is great. I love strip tillage. I'd like to think that if I were a farmer, that's probably what I would do. And we don't have to get into the idea, we don't have to get into all the whys, but I like that system in general. But the facts is it's expensive. It's logistically complicated. It takes longer to apply the fertilizer. You have to have enough manpower. There's a lot of buts. And I've talked to a lot of farmers that tell me they love strip till, tell me they've seen the advantage, but they've grew and they don't have the time and manpower to get it done, so they don't do it, okay? I can also tell you in my research plots that when I apply all the mineral nutrients on the planter, because I can do that, I don't have to get 1,000 acres done, so I can take the time to do that, I see maximum yields when I apply all that fertilizer with the planter, relative to 15-inch dribble banding, and even much more so to broadcasting dry fertilizer, okay? So I can tell you that in my experience that if we can apply all those nutrients where the plant's going to be, we get higher yields. Okay, so the university, I showed you a couple of university studies, and I will tell you from my studies with the planter that happens. But it's the same problem with the planter. Who has time, or who has time and who wants to manage the logistics of putting on 30 gallons of material with a planter? It's just hard. Okay, so what's a more cost-effective and logistical way to get this done? So that's where we came up with this idea of exact strips. All right, so the idea here is we share RTK guidance lines. We get the guidance lines from you that maybe you already have made. We put those in the floater, we follow those guidance lines, and we apply that fertilizer where you're going to plant, or close to where you're going to plant. Is this system perfect? No, it's not. In fact, 2 years ago, we started doing this with a few people who strip till, and only because we wanted to be able to measure how far off the center of a strip till band did that suspension fertilizer actually get placed, okay? And over about 3 fields that are reasonably flat, mind you, we were able to get with plus or minus 3 inches of the center of that band. So that's thinking about what kind of nozzles do we need to use. That's making sure that the floater was calibrated, the farmer's equipment was calibrated. That's making sure the guidance lines got shared and converted appropriately. There's some steps involved, but we can do it, and we prove that we can do it, okay? And Chris Tinsman is the guy who's done a lot of the technology integration with sharing the guidance lines. He's the expert at that, and he is obviously on our staff and can help our retail guys and our customers share that guidance information appropriately so things do line up. I'm going to play a video here. So this would be our Traer location applying suspension fertilizer on top of strip till bands there. So again, we're doing this on top of strip till bands in this situation so we could physically measure where the fertilizer was relative to the center of that strip. So this is a Terragator at DeWitt. So in this instance, we actually mounted a GoPro camera right above one of the nozzles so we could visually observe. This is for us so we can see how close are we. This video goes on for like 3 minutes, but you can see in that 3-minute period, we're pretty close. Even on the end rows where he turns around, you can see that where the fertilizer was already applied, even on the end rows, that band of suspension was pretty near in the center of that strip till mark where the farmer went through and previously strip tilled. So this is at our Clear Lake, Iowa location. You can see the potash crystals laying on top of the strips. So I don't want us to pigeonhole this just into strip tillage. Okay, it clearly could be a way to help strip tillers get things done quicker. But in this instance, this is at DeWitt, Iowa. In this instance, the farmer took a one-pass tool across that field. We applied the fertilizer, and he's going to stale seedbed plant back into that this coming spring. That worked for him. In this case, this is at Roseville, Illinois. So in this case, we followed an anhydrous toolbar. So in that case, the farmer is going to plant back into that anhydrous and P and K band come next spring. So I don't want to pigeonhole this into just strip tillage. And I think if we're doing somewhat minimal tillage, that could even be a good thing with these 30-inch bands because we're distributing that fertilizer across a little larger surface area, which can be good for maximizing nutrient uptake. And I don't have time to get into that, but I don't think a little bit of tillage on top of these bands is actually a bad thing at all. In fact, it could be a good thing. Okay? So in addition to all this technical stuff we had to figure out, I'm doing small plot trials to try to understand, agronomically, how close do we need to get? When we went into this, we didn't know how close we could get. So we also needed to know agronomically how close do we need to get. So this is the average of 3 locations from last year. So just like the University of Illinois study, I applied fertilizer at 0, 3, 6, 9, 12, 15 inches. I had a broadcast treatment and a control with no fertilizer. What we've seen is that the 9 through 15 inch band yielded about as much as the broadcast, and once we got to about 9 inches, we started to see yields creep up. So the maximum difference was 9 bushels between broadcast and 0, okay? This is at one of the 4 locations. So at one of the 4 locations, there was no difference in yield between the band and the broadcast. So back to my comment early on, not everything works all the time, and this surely won't work all the time either. But 75% is pretty good. And I think with the university data I showed you, I think with the 3 locations that were very successful last year, I'm pretty confident that going forward, the trials I have in the field right now will see the same type of trend. There are a lot of questions to answer, though, yet on my part about different tillage situations. You know, if we're doing this with a strip tiller, should we apply these fertilizer bands before the farmer strip tills, or do we do it after the farmer strip tills? There's a lot of questions yet to answer here. Spring versus fall, for example. There's a lot of questions to answer, but I'm confident we're headed down the right track with this. There's one last thing I want you to think about, and it could be very relevant to this geography in West. So the problem with potassium is this. So this would be the percent of relative corn yield, and this would be the potassium level in the soil, okay? So what we can see there is there's a whole mess of variation, all right? So sometimes at 100 part per million, shoot, we can maximize corn yield, right? But sometimes at 250 part per million, we don't even maximize corn yield, right? So the point is that, yes, that would tell you that as we get higher potassium levels, we tend to get closer to maximum yield. But it will also tell you that unless you have 200 part per million or greater, you can't guarantee you're going to maximize yield. And when I look at the soil tests from across our company, as well as competitors, and what the state reports, potassium in the state of Iowa is the mineral nutrient that keeps me awake at night, okay? About 50% of the samples that we collected from 2007 to 2015 are below 150 part per million. There's only about 20, and there's about 25% that are between 160 and about 200 part per million. So it's that 160 to 200 that's the gray area, okay? Anything below this, we would absolutely expect a profitable yield increase. Anything in here is a gray area. In years where it's very dry and we got lots of that potassium stuck in those inner clay layers, we would absolutely expect a yield increase at that level. And there are some samples, about 25%, that are above that 200, 225 part per million. But the question I ask is, who can afford to go from 100 part per million or 125 part per million to 200 part per million? No way. Not with fertilizer prices where they are, okay? But you got to think about it this way. If you have enough money to spend on 100 pounds of potassium per acre, and you apply that 100 pounds of potassium on an 8-inch area of the soil, and you incorporate that to a 60-inch depth, you're going to raise your soil test levels by 44 part per million. If you take that same 100 pounds of potassium and you broadcast it across the 30-inch row, and you incorporate it to a 6-inch depth, you're only going to raise your soil test level by 11 part per million. So you can raise your soil test levels a lot quicker by focusing those mineral nutrients on a given area where you're going to plant your crop, where most of those mineral nutrients are taken up. So you can cheat the system by focusing on applying mineral nutrients where you're going to plant your crop. All right? So that's the last thing I'll say about RTK banding. Are there any questions? 42 minutes and 54 seconds, Katie. Write it down. Yeah, that's a great question, Jess. When I went into this thing, so Jess asked at the locations where I did the RTK banding, how many of the locations were worked? So what was tillage done, okay? This location was a sandier soil right here where we didn't have any response. Okay, I was actually quite surprised that there wasn't, because in a sandier soil I would assume this actually is very good, but there was not a response at this location. There was chisel plowing done in the fall, followed by spring field cultivation. Okay. At these three sites, one of the sites was true no-till. Two of the sites was fall chisel plow, followed by spring field cultivation. The direction I gave the farmer was, I want you to chisel and field cultivate with the direction I'm going to plant my rows. You know, I didn't want him to go across and spread that stuff out too much, but I said, I want you to do your normal tillage, and I want you to go with the direction of the rows, okay? At two of those three sites, we saw this trend. Two of those three tillage sites, we saw this trend. At the no-till site, we saw this trend. I am not at all convinced that tillage, some amount of tillage can't be done and we won't see this. I don't know if we want to get into the gory details of this, but you can band too tight, right? So, you know, what I'm trying to say is you can't ask a very small area of roots to take up all the mineral nutrients that the crop needs. It's actually a good thing to disperse those mineral nutrients out to some extent. And this is rooted, what I'm telling you is very rooted in science. I'm not just up here making it up, okay? But if you had to pick, you would want to concentrate those nutrients in about a 6-inch area at about 6 inches deep. You want to spread those nutrients out as much as possible over the given root area, because roots are more efficient. Roots can only take up a certain quantity of mineral nutrients so fast, okay? So the idea here is, in an optimum world, in the perfect world, you try to spread out those nutrients over that root area, but yet still keep them concentrated. So that's not why I'm convinced that tillage is necessarily a no-go here. And that's actually why I think with our 15-inch dribble bands, we still see responses when we do tillage, because we're moving those dribble bands around in a way that we still have concentrated nutrients, we're still getting the benefit of the banding, but we're moving it around enough that we still can maximize nutrient uptake, if that makes sense. So that's why I mentioned I still have some studies to do to understand how important tillage is or what types of tillage can or can't be done. But to answer your question, at two of those three sites, there was fall chisel plowing done, followed by spring field cultivation. Thanks everybody for your time.
Lead Academy, Liqui-Grow,
Excellence
and agronomy
development.